In this video, I'll be working through the question you can see on the screen here from the summer 2025 Cambridge A-Level Maths paper 3-2. I'm going to try and show you how to do this question and not just the solution. So you may need to pause and rewatch certain parts of the video. If you're looking for a different question from this paper or a different paper entirely, you should be able to find a playlist in the description below or have a look around on my channel. Okay, let's get into the maths. In question 10, they ask us to find the quotient and the remainder when x squared is divided by 1 plus 4x squared. So let's write that down. X squared is divided by 1 plus 4x squared. There's two ways I can do this question. I'll do both of them because they're quite short. The first one I think is probably the shorter one, but it's probably the harder to think through. We need to recognize that when you divide something by something, it goes in a certain number of times. That could be 0 times, could be 1 time, could be 8 times, it could be a half times. So we'll just call that some number here. We'll call it, I'll just call it A. Any letter you want. This is going to be the quotient though. So I guess you know what, let's call it Q, because it's going to be the quotient. Then it's also going to have a remainder. Maybe maybe the remainder is 0, or maybe the remainder is 8 or whatever. It's going to have some remainder, and we write that as the remainder divided by this. Whenever I have trouble sort of remembering how this looks, I just think of a simple example like 8 divided by 3. 3 goes into 8 2 times plus 2 remainder, and that's 2 divided by 3 would make this make sense. 2 plus 2/3 is 8 over 3. Just like here, it goes in a certain number of times plus a remainder, and we write the remainder divided by that to make the equation work. We can just solve this. Multiply everybody by 1 plus 4x squared. We're going to equate like terms. Multiply everyone by that. The left side just becomes x squared. Q is the only one that gets multiplied. We get well, let's do them by out. Q times 1 is just Q. Q times this is 4q x squared, and this just becomes r. Like terms, just equate like terms. X squareds must equal the x squares. So that means the 1 in front of this must equal the 4q in front of that. Or rearrange that, it must mean q is equal 1 over 4. That's the quotient. That's how many times this goes into this. 1/4 times. The second way I'm going to do it will show you that a bit more clearly as well. What's the remainder? Well, just equate the terms again even. There's 0 number terms on the left. There's q here, which is 1 over 4 now, plus r. So r must rearrange it, move that over, we just get r is equal minus 1 over 4. There are your two answers. You didn't have to write it out like this. Just have to do this little sum. Q is 1 over 4, or the quotient is 1 over 4, and the remainder is minus 1 over 4. Another way you could do that, my personal favourite, because I love doing long division, although this isn't really that much of one. We've got x squared and we're going to divide into it. I'll rewrite this though as instead of 1 plus 4x squared, I'm going to write it as 4x squared plus 0x's plus 1. And instead of x squared, I'm going to write that as plus 0x plus 0. Whenever I do long division, it's really good to write them out, first of all in the correct order, the same order as each other at least, and with all the missing terms put in as a 0. So how many times does this divide into this? Well, we just look at the first terms. What would you have to multiply this by to get this number? You'd have to multiply this by 1 over 4, and that's where we get the 1 over 4. So you could do it as simply as that. You could do that in your head, in fact. Get the quotient, and then we just multiply 1 over 4 by all of this. This becomes x squared. 1 over 4 by that becomes 0x's. 1 over 4 by 1 becomes 1 over 4. Take it away and we find our remainder. No remainder there, no remainder there. 0, take away this, it's minus 1 over 4. There's your remainder. So again, it was quite easy and straightforward both ways. I guess there's only 2 marks for that. Still, I think it was a good, clever question, that. If you are finding my videos useful and would like to help the channel out, on top of liking and subscribing, probably the best thing you could do is to tell other people doing the exam about my channel. Maybe you could share this video in a class WhatsApp group. Then if you feel I've really deserved it and you would like to buy me a coffee, you could become a member on YouTube or on Patreon. You should find links to that in the description below. And next they give us part B, which doesn't look related whatsoever, but a hint that it is. I've left the previous answer from part 1, at least roll a different way, the quarter and the minus quarter. And I say hint there because definitely part A is a hint how to do part B. Maybe you should be racking your brain to think, how are these related? Because this is a hard question to do. I'm going to just give you my thinking on it and hopefully help you in a few different parts where we have to take a leap. Because often maths, especially difficult maths like this, is we can all learn how to do the different parts, but there's multiple parts where you're going to have to take a leap to figure something out. I think this is one of those questions. So what is that leap here? Well, how do we do integration? There's a couple of different ways we can do difficult integration like this. The two main ones that we're going to think on here is substitution and integration by parts. Now in both of them, we end up differentiating part of it. So whatever we substitute, we end up differentiating it. And so differentiation is important. And what should be jumping off in your head a little bit is inverse tangent. So you could get stuck up changing this into sine and cosine and trying to do it that way. It's not going to work. Inverse tangent of something. We have a formula for that. We know how to differentiate that. And importantly, we don't know how to integrate it. So that's a great hint. Maybe we could substitute this out and differentiate it. Let's write the derivative of it over here anyway. It'll be useful to have d dx of the inverse tangent of x is equal to, what's it, 1? Yeah, okay, 1 over 1 plus x squared. We know how to differentiate something that looks a lot like that. And the answer, 1 plus x squared, that's starting to look somewhat similar to what we had at the start. Now, it's okay if you don't put that connection together yet, but still, we know maybe some differentiation here is involved. Let me just think through substitution. Again, it's not going to work, but if we were to substitute this, we would end up getting this as a derivative. And then we would end up dividing by this, which means multiplying by this bottom row. So we would have x multiplied by that. That doesn't get rid of anything. It still leaves us a bunch of x's, and we'd have this new substitution of u. So substitution's out, unfortunately. It looked like a good way, so it's okay if you tried that. Don't feel too bad. It's a good thing to have tried, even if you've gone through a few lines of it. But you will get stuck. It's not the path to take. The path to take here is integration by parts. Let me write the formula for that down here. When we have two things multiplying, a u and v often, or u dv we write. I'll explain why in a moment. We can rearrange that. Think of this as just two things, a u and v. One of those things has a dx on it though, is what we have here. So maybe it's u is x maybe, and v is this whole thing with the dx. That's why we have the dv. Or maybe switch them around. It's maybe that's the u part I'm covering up, and the dv is x dx. Okay, anyway, if we have two things multiplying, we can rearrange it so it's just u times v, and we get the we evaluate that, minus the integral of v du. Basically, you can think of this as, this is too difficult. How about we change it to make this one, and hope, really hope, that this one's easier to do. And it will be in this case. So what I like to do there, I know students have like a list of things to go through for this. All I like to do is I write uv and du dx. You don't have to put the dx in if you can think it through in your head. Dv dx. I like to fill these in. Which is the u and which is the dv dx of the two choices here. So basically, does x go here, or does the inverse tangent go here? They're your two choices, and the other has to go here. So it could be x inverse tangent. Now it's not going to be inverse tangent here, because let me just write it in. The inverse tangent of 2x. Because once you get here, you need to find out what v is. To do that, you need to integrate this. And we can't integrate this. That's the whole point. That's the trouble we're having. So it's not going to be that. So the u is going to, I don't have enough room here, let me clean that up. The u is going to be the inverse tangent of 2x. And that means the v part must be the x. Just the x here. And the reason I write it like this, because I think it's just easier to see, but we can move the dx over. And that's where this combined with this gets this whole line. Okay, it's just, this is more just something to help me think it through, what u and v is. Because we can integrate this. The integral of x is just x squared divided by that 2 there, divided by 2. And we can differentiate this. It's nearly this. It's not quite 1 plus 1 over 1 plus x squared. Because x is 2x now, so it's 1 plus 2x squared. But we had to use the chain rule there. This is cheating. We cheated by putting that 2x in. So we have to fix our cheat by differentiating this and multiplying. So we multiply by 2. And that's this 2 in here. The derivative of this is what we're multiplying by. Now it's still not obvious at all that this is the right path. Often when that's another really difficult thing about this question. Often when you start down the path of integration by parts, we go, oh, this was working. I've got something here. In this case, it's not obvious at all. We're going to end up with this multiplied by this, and we still have to integrate that. Nothing cancels there. We'll have an x squared divided by a 1 plus 4x squared. That doesn't cancel. But that's where the part 1 comes in. This is what we'll end up with. So we can't integrate this, but we can integrate over here. Let's write it out. So this whole thing now becomes true integration by parts. This whole thing becomes, let's name this I. This whole thing I becomes u times v, which is just the inverse tangent of 2x multiplied by x squared over 2, and that's evaluated between 0.5 and 0, minus the integral of v du. So that would be x squared over 2 multiplied by 2 times 1 plus, let's see, 4x squared. And this is still between 0.5 and 0. We're still not done, but we're now looking like this could be a path. The 2's cancel. X squared divided by this. If you were unsure you were on the right path, looking back to part A should convince you, yes, I'm on the right path here. Like, why did they ask that in part 1? What has that got to do with the rest of the question? We now know we're on the right path. Okay, I'm going to clear everything off the board and we'll just start. Actually, you know what? We'll just do this question here and then we'll put this back in to save a little bit of ink. Okay, all of that work got us to this point. The integral of this is the same as this number here minus this integral. So let's try and do this integral here. It's not as bad as it looks. First of all, I'm going to save a bit of room because I don't want to write this every time. I'll cheat a bit. You guys can pause, rewind, so please forgive me for this. This here is identical to this, so let's replace that. This becomes 1 over 4 minus 1 over 4. Well, let's take the 1 over 4 out actually. 1 over 4 comes out here. 1 minus 1 over 1 plus 4x squared dx. This is a lot more manageable than the previous one. So let's try and do this. First of all, 2 integrals. The first one's not too bad. I'm just going to have to write this loads of times, I guess. X squared over 2 inverse tangent 2x. The integral of 1 is just x. So this becomes minus a quarter x. Then the next integral is minus by minus, so that's a plus. There's still a quarter here. And we have the integral of 1 over 1 plus 4x squared. That's dx here. We've already done a few hard integrals in this question. We're left with another hard one. In fact, this I'd say is maybe the hardest one. A lot of students are probably going to get to this point and get stuck. Because you could try substitution. it's not going to work. You could try integration by parts, it's not going to work. How do we integrate this term here? The answer is actually shockingly easy. I sort of had the answer up on the board previously. We used the answer previous in the question. We already said the derivative of the inverse tangent is 1 divided by 1 plus something squared, or x squared. The opposite is true. If you get from, it's right here, inverse tan, the derivative of the inverse tan goes to 1 over 1 plus x squared. The same is true the other way. If differentiation goes this way, integration goes that way. The integral of this is equal to that. The integral of this is nearly equal to tan, and we had it exactly earlier. If only there was a 2 here. That was the answer when we differentiated the tangent earlier. We got a 2 divided by 1 plus 4x squared. If only there was a 2 here, it would be easy to go backwards. So let's just put 2 there, and we'll fix our little cheat by putting a 2 out here. That means this, let's continue on over here. We'll have x squared, I'll just write the whole thing again. X squared inverse tangent 2x minus 1 over 4x plus 1 over 8 now. And the integral of this just becomes inverse tangent of not x but 2x, because we get 2x squared down here, and that's where this 2 appeared from as well, of 2x. That's all of this. Let's put a big bracket in here. All of this is evaluated between 0.5 and 0. That's what we're pretty much done. That's the integral of this original mess they gave us. All we have to do is fill in these numbers, and it's not as bad as it looks. 0.5 multiplied by 2 is 1, so the inverse tangent of 1, and that's just pi over 4, or 45 degrees. But we'll stick with radians. That's just because I assume this is radians, because they're going into actual numbers here. So if there were degrees going in, if we wanted degrees out here, we'd also want degrees out here, which means degrees would have to be up here. But anyway, they want radians. I'd say they'd find a way to give you marks if you put in degrees. The inverse tangent of 1 is pi over 4, but also has to go in here. This is a half squared. That's a quarter, and that's a half of a quarter. So that's 1 over 8. That's pi over 4. 1 over 2 multiplied by 1 over 4, that's another 1 over 8. Plus 1 over 8, and this is pi over 4 again. Put 0 in. The inverse tangent of 0 is 0, so you're done. Put 0 in here. 0 multiplied by anything? 0. You're done. Inverse tangent of 0, you're done. Zeros didn't matter. You don't have to take anything away from it. This is our final answer. 1 over 8 and pi over 4, what's that? That's 1 over 32. Another 1 over 32, that's 2 over 32. That's 1 over 16. Pi over 16, I guess. 1 over 16 multiplied by pi, or pi over 16. Take away 1 over 8. That's it. That's our final answer for, I don't even know what question we're on. Question 10. That was easily the hardest question in this paper, I think. It took, in maths, there's often we can just do work. We'll just do work and find the answer. In this question, I think we needed to take leaps. And you often have to take a leap. That separates the people who get 80% from 90 from 100. This question alone, I think, had about 2, probably 3 leaps of knowledge. You had to recognize that the integral of this is tangent. You had to recognize that integration by parts does the question. I guess you had to recognize that the part A helped in part B. It was a hard question. So if you have any follow-up questions for me, please put them in the comments. I'll do my best to answer you. Thanks for watching and have a great day.